Hi everyone, welcome back to E54. Today we're going to be doing lecture 5, and our topic of discussion is going to be diffusion. So when we talk about diffusion, what we're really talking about is material transport in our material through atomic motion. So those atoms inside of our crystal structures can rearrange, and this turns out to be really important for many properties. This includes things like when we process materials, it's important, and then also as we go and use materials in real life applications, diffusion comes into play. So I want to point out that diffusion is neither inherently good or bad. Sometimes it can enhance properties. An example, and we'll talk about this one, is you could do what's called carburizing a surface, where you're trying to diffuse certain elements into the surface to make your material harder and more wear resistant. In contrast, diffusion can lead to degradation. So you can have reactions that happen at interfaces, which degrade the surface properties of your material. So some of the key things we're going to talk about is we're going to try to understand the mechanisms through which diffusion occurs, how it pops up occasionally in processing, how we can go and predict the rate of diffusion for some simple cases, and then also how diffusion depends on the structure of our material, temperature, and a few other things, okay? Now, it's important we're gonna talk about a few different mechanisms. When you're talking about gases and liquids, you tend to have diffusion by random Brownian motion. We're gonna be more focused on solids in this class. So we're gonna talk a lot more about diffusion through these two mechanisms of vacancy and interstitial diffusion. So diffusion is time dependent in many cases. What I'm showing here is sort of two examples of how you can visualize this. So on the left side, I have something where we have some gas with a higher concentration than the gas on the right. And we can think about having some unit area, maybe this is a membrane or something like that. And we're thinking about how much gas is transferred through there. In contrast, you can think about the situations as what's drawn here on the right. You can either have this be gases or solids, but you could think about putting two blocks of pure materials next to each other and then allowing them to mix. And one thing, for example, you might want to know is what's the concentration as a function of depth away from this interface as you let that experiment go on. And a practical place that we see this is in things like gears. So something called case hardening is where we actually intentionally diffuse carbon atoms into the host iron material at the surface. And we'll talk about this mechanism, but this is actually interstitial diffusion. And the idea here, this is a gear that there's been a section cut out. And the concept is that your inner material is different than that material right on the surface. This material by itself is relatively strong. And you wouldn't want your whole system to be made out of that because it might also be brittle, okay? But you just want the surface to have different properties. So for example, where these gears touch each other, you want it to be very strong and not have material deforming or material wear away. You can see the more high-tech applications as well. A common one is in computer chips and things like that. So for example, we make these chips by taking silicon and doping with different materials. And if you dope with phosphorus, you'll end up with an N-type semiconductor. And we'll talk about electronic properties later. But the basic idea is you take your silicon wafer, you deposit phosphorus in these regions or layers where you want it. We're showing a 2D slice here, but it might be some more complex device structure, as the figure on the right is showing in the top-down view. You go and you heat this sample, and then what happens is what was originally on the surface diffuses into your material, and then now you have these regions beneath the surface which are doped with the phosphorus, and it changes their properties. On this slide, what I'm doing is showing what's called a diffusion couple. This is, again, that very simple type of experiment where I take a block of pure copper and a block of pure nickel. You can do this with different materials too. Originally, you could see all the atoms are copper on one side, all the atoms are nickel on the other side. And another way of looking at it is I could draw what's the concentration of each in a given region. So on the left side, it's 100% copper. then we have this step function that goes down to 0. Nickel is the opposite. So it's 0% nickel, and then it jumps up to 100%. So it's this very discrete change. If I were to give this system some time and temperature, that region in the middle near that interface would become very different. Atomically, I could look and see that sometimes the atoms are red, sometimes they're blue here. And if I looked at the composition, I would now see that I don't have that abrupt or discrete change. I now have a more gradual change from 100% to 0% copper and from 0% to 100% nickel. And what I'm showing on this slide is that same variation. So that original step function, how we have gradual diffusion. And if we give this thing infinite time, what we eventually get is a 50-50 mixture of our material, okay? Now, the other thing that's shown on here is that the real way these atoms end up switching spaces is through the movement of those vacancies that we discussed in the last few classes. Those turn out to be very important. So you can have many different types of diffusion. One of the types is what's called self-diffusion. So this is, even if I just have a system which is all the same type of atoms, it doesn't really matter what, but let's say that these are all copper. If I look at it before and after, it looks the same. So in this case, all the atoms are in a lattice and it looks like nothing changed. But if I were to somehow label and track the atoms, I would find that these 4 I labeled, A, B, C, and D, have shifted around and changed places inside of that material. So we can have diffusion with the self-diffusion, or we can have things mixing like we mentioned before. Okay, so let's start talking about mechanisms. One of the first ways that diffusion can happen is through what's called vacancy migration. So what I'm showing here on the right side is a set of atoms on a lattice. There's one vacancy in the system. You can think of this top picture as time 1, the bottom is time 2. And right here, this vacancy is originally in this central location. And as time goes on, this blue shaded atom is going to jump down and fill that space. And when it does it, it leaves an open space behind it. Okay. So you can think of this 2 ways. If you wanted to sort of keep your eye on where the vacancy is, you could say the vacancy has gone from here to here. So the direction is up and to the left. In contrast, if you wanted to look at what the atom was doing, the atom went down and to the right, okay? So the atom is traveling in the opposite direction of the vacancy. They exchange places. And this is just showing how that can lead to variations across those diffusion couples. So if instead of drawing it perfectly with all the atoms and all the lattice positions, I have a vacancy in this original one, you can imagine one of these orange atoms jumping into that vacancy moving into the other crystal. It jumps up, that atom switches, and eventually it gets up here and it goes back into that gray crystal, and that gray atom came over to the left. Now what's happened in all of these jumps is that you end up having one orange atom in that crystal on the right where there originally were 0, and this gray atom is going over to the left. Now, these atoms exchanging with vacancies ends up being pretty important. In addition to self, it can happen with substitutional impurities. And this rate at which this happens is going to depend on a few things. The most obvious ones are how many vacancies I have. So I'm showing you this example with 1 vacancy. You can imagine if I had 100 vacancies in the system, this process would happen a lot faster because each one of those can cause some effect. And we care about what the activation energy is to exchange. So how hard is it for these 2 to switch, the vacancy and the atom to switch? On the right here, this is just showing an atomistic simulation. So here you see a much larger crystal. There's many more vacancies, and we're going to have these things jump around with a certain probability. This is actually what's called a Monte Carlo simulation. So these atoms are jumping around. You can see those vacancies sort of randomly jumping around. And as they do, atoms are moving in the opposite direction. And gradually over time, this interface, which was perfect, starts to mix in. So you can see clusters of blue atoms which have moved to the left, and then clusters of red atoms which have moved to the right. Let's play this one more time. So if you think about this type of simulation, if I added more vacancies, that process would be faster. But also if I had those random jumps happening more frequently, that would increase my rate of diffusion. Now, it turns out that that frequency of that jumping is pretty directly tied to temperature. Another diffusion mechanism we want to talk about is interstitial diffusion. So in addition to just atoms jumping between lattice points, if we have interstitial impurities in the system, those can jump around as well. And this turns out to be much easier than that vacancy-driven diffusion. So this is showing how this orange atom is able to jump from one relatively open space to the next. And you notice that no atoms really had to switch positions. It's just able to jump around in these relatively open spots. And this is showing a more detailed path. So this black atom is at the top left of our crystal originally. It jumps around in patterns that are sort of random. And over time, it ends up some distance away. It's sort of randomly just jumping around, but the net migration after these end jumps is down and to the left. Okay, so let's start putting some equations and numbers on it. So the rate of diffusion that we see can be quantified in terms of diffusion flux. So we'll use the term J for this. And this is just the mass diffusing through and perpendicular to a unit cross-section area per unit time, okay? So if I had that drawing before where I had some unit area, how much matter is coming through that region, okay? And that flux is just that mass normalized by the area and the time, okay? So it might be something like grams per meter squared second. Now, if the diffusion rate doesn't change, which is very common in solid materials, especially, what we're going to find is that we can get a steady state condition. So you can think about measuring this empirically. Maybe you make a thin film. That's going to be our known surface area. You're going to impose a concentration gradient. Maybe you have more of atom A on the left than on the right. And you can measure how fast atoms or molecules diffuse through that membrane. So if you think about rearranging or showing a different way, that flux, if that area is constant, is just going to tell us what's the rate that mass is diffusing through that region as a function of time. Okay? So if I ran that experiment and I plotted what's the mass diffused versus time, it might take some time to start, but once that diffusion process starts, it's going to increase with a slope that's proportional to that flux. Okay, there would be that unit of the 1 over area in front of there, but it would be proportional to the flux. We can use this type of description in many ways. What we really want to often know is what's the concentration of that diffusing species as a function of distance, and we could call that the concentration profile. So how does it change as we move toward and away from that interface? And then if you want to, you can also talk about the slope of that concentration profile, and at any point that's going to be called the concentration gradient. So that flux is also proportional to the concentration gradient, so the derivative of concentration with respect to position. And this is how we end up with Fick's first law of diffusion. Okay? So it says that the flux is equal to negative our diffusion coefficient times that derivative dc dx. Okay? And let's sort of use this really simple type of example. On the left, the material has concentration C1, which is larger than concentration C2 on the right. And if we want to describe how it changes in this region, if we know sort of what our bounds are, so C1 and C2, and we know the distance over which it changes, then that derivative of C with respect to X just becomes a change in C divided by the change in X. So it could be C2 minus C1 divided by X2 minus X1. So it's just finding the slope of that line. So again, this is talking about what's that net flux. That D is diffusivity or diffusion coefficient. Those words can be used interchangeably. It has the units of some sort of area, so it could be meters or centimeters squared, and then per second. Now, one thing I want to point out real quickly is that that negative sign is important because it tells us that the diffusing species is going from higher to lower concentration. You can think back to that example I gave of putting pure copper next to pure nickel. Eventually, they're going to want to mix and become 50-50 concentration. So we can think about a few types of places where you could deal with these type of problems. So one place, for example, if I were to describe a problem where you had to work with this methylene chloride, which is a common ingredient in paint removers, and you don't want that chemical to irritate your skin, so you wear gloves. So if you knew that this thing, you want to keep it away from your skin, you knew what gloves you had and how thick they were, you could go and calculate something like what's the flux of that chemical through the glove. So to know that, to go and calculate this, you would need to know a few things. You would need to know what's the diffusion coefficient of that chemical in that rubber glove. You would also need to know what the surface concentrations are. I'm just giving you values for these right now. So maybe this 0.44 grams per centimeters cubed is the concentration in that paint thinner. And then that 0.02 is what I could define as the acceptable concentration at my hand. So I know I don't want it to be higher than that. And then I could go back to this little drawing I have, and that high concentration area is the paint remover, the low concentration area is my skin. You could want to describe what flux is happening through that region in the middle. You would need to know something like what's the diffusivity that was given in the problem. You were also given C2 and C1. And then the last thing we would need to know is X1 and X2. And it turns out that that's just going to be the thickness of the glove, right? So that change in X is going to be how thick that glove is. So we could just go in and do a pretty straightforward calculation, plug in those numbers in that equation, and end up describing that in this case, the flux is 1.16 times 10 to the negative 5 grams per centimeter squared per second. That number doesn't mean all that much, but I'm just trying to show that this is a way you can use this simple equation and put it into a more practical type of situation. So we mentioned that both the number and the frequency of jumps is very important. So one of the major places we see that is that the diffusion coefficient of a material increases very strongly with increasing temperature. And it does so in a way that follows that same type of Arrhenius law that we saw before. So the diffusivity of a material is generally going to be equal to some constant. We're going to call this D naught, multiplied by the exponential negative Q sub D, which is the activation energy for diffusion, divided by the gas constant times the temperature. We already saw this equation before, but we're just applying it to, we saw this for equilibrium vacancy concentration. Now we're applying it to diffusivity. So this is some real data. You could go and look at what the rate of jumps per second is plotted against inverse temperature. And this is on a log scale on the Y, which means that small changes in the vertical direction are big changes in the diffusivity. So these are labeled as order of magnitude changes. And this slope of this line is going to be just Q divided by R. Okay. We often don't see it in terms of rate of jumps. We see it more in the practical measurement of this happening, which is the diffusion coefficient, but you see the same thing. So you, on a log versus inverse temperature plot, you see this straight line of the data, and you can see that moving in the little amounts on the x-axis gives you huge changes in your diffusivity. So you can go from something times 10 to the 16 to almost 10 to the something times 10 to the minus 13. So that's 1,000 times change in that property. So that activation energy shows up there as well. So if you think about it for the same temperature, if you had a lower activation energy, it would be very easy for those jumps to happen. So we talked about two mechanisms, the substitutional and interstitial type of mechanisms. And we can think about how that relates to that activation energy. So in either case, so if this blue atom right here is going to jump across and fill in that vacancy, or this interstitial is going to jump through this relatively open space and find another interstitial site, what would have to happen with these atoms? Well, in one case, this atom is going to have to cross through and be very close to the atoms above and below it. Okay. And in the other case, this interstitial can find a little meandering pathway through that open space. So it turns out that that manifests in that energy required for this event to happen too. And the energy for that vacancy migration tends to be higher than the energy for the interstitial migration. This little simulation is just showing an interstitial shifting around in those empty spaces, and that motion and that mechanism it takes is going to be related to the barrier for diffusion. And that shows up in these material properties. So let's look first at this plot on the left here. So this is diffusion coefficient versus inverse temperature. Again, the slope of that gives me an activation energy. But more importantly, we can look at what's happening in different classes of materials. So for example, many of these are substitution or sort of self-diffusion through a substitutional vacancy mechanism. So for example, aluminum diffusing in aluminum matrix. And we can compare that with a tiny carbon atom in an iron matrix, okay? And what you can see is that for a given temperature, the diffusivity of that carbon in iron it's about maybe 10 to the 12 here. And if I go down, it's 10 to the 16 or 10 to the 15. So it's again, at least 1,000 times smaller. And it turns out that that's actually pretty surprising. So aluminum melts at really low temperatures. So the fact that its diffusivity is lower at the same temperature really shows the effect of an interstitial versus a vacancy mechanism. Right? And those slopes also correlate to that activation energy, remember? So the fact that this has a shallower slope means that that activation energy is lower than this steep slope. On the plot on the right, this is showing the same type of data, just many, many more materials. So it's more sort of random type of thing. So it's uranium and uranium oxide, it's oxygen in a copper oxide. But generally on plots like this, sometimes you'll see this legend, which tells you how that slope actually correlates to something physical. And this slope actually means is connected to the bonding of the atom in that system. Okay, so if you see a steeper slope, means that there's stronger bonding between the atoms, and a shallow slope means it's really weak bonding. So let's see how we can use this. So, for example, I could give you a problem that says, well, at a certain temperature of 300 degrees C, the diffusion coefficient activation energy of copper in a silicon material are these values. So the diffusivity is 7.8 times 10 to the minus 11. The activation energy is some value. And with that, I could say, okay, what would the diffusion coefficient be at 350 degrees C? You could think about what that data looks like. You know that diffusivity is going to be exponential with temperature from our Arrhenius law. Alternatively, you could think about it being a straight line on that natural log of diffusivity versus 1 over temperature. What we can do is take those equations for each temperature. We can have a diffusivity. So what I did here is I took the natural log of both sides. So this was originally D2 equals D naught exponential negative Q over RT2. So what I did is I took the natural log of this and I subtract it from both sides. And I can end up getting rid of some of those terms. So specifically, I'm getting rid of the D naught. And I'm starting to reorganize this. So I have D2 and D1, T2 and T1. And as you can see from this figure, I know what D1 is, I know what T1 is, and I'm asking you what the diffusivity is at T2. So I've given you that too. So you just end up solving for D2, right? We can start plugging in some numbers. One thing I want to point out is we're plugging in temperatures here. We again have to remember to use the absolute temperature. So I said that the temperatures were 300 and 350 degrees C. Degrees C doesn't work here. If I plug that in, I'm going to get the wrong answer. What I need to do is put this in terms of Kelvin. Once I plug that all in, I can go and solve for the diffusivity. In this case, our original value was 7.8 times 10 to the minus 11. So that diffusivity has doubled. So it's gone from almost 8 to almost 16 with just a small increase in temperature, so 50 degrees Celsius. So that activation energy for the self-diffusion, I mentioned it correlates with bond strength. And one way you could see this is if you were to take and make a plot of the activation energy for that self-diffusion versus the melting temperature, which we mentioned is correlated with bond energy in one of our earlier lectures, you would find that as the melting temperature goes up, the activation energy for self-diffusion goes up as well. So let's do a practice question real quick. So the question is, the diffusion rate increases with all of the following except, right? So that tells me that only one of these is incorrect. Let's go through and sort of check them one by one. So the diffusion rate, does it increase with increasing temperature? Well, yeah, we mentioned how those vacancies can have more frequency of jumps and that can lead to higher diffusion, okay? So that one is true. That's not our answer. Lower density. Well, we mentioned that diffusion happens when atoms jump around, and that's easier with open space. So if my density is lower, it's easier for that diffusion to happen, okay? That one's not the answer. Weaker atomic bonds. Well, I just showed you that stronger bonds lead to slower diffusion. Okay, so that one's not the answer. Closer packed structure. So in a sense, this one is the opposite of low density. It's saying my atoms are packed in a way that there's not much open space. Okay, so that's a candidate. And then finally, smaller radius of diffusing species. Well, if diffusion is happening when that atom is moving around, it's going to be easier if it's really tiny and it can find a path. Okay, so our answer is going to be D. That closed packed structure does not give us a faster diffusion rate. In fact, reduces it. What I'm showing here are some different dopants in silicon. Again, this is very important for microelectronics and things like that. And generally what's happening is as the atoms are smaller and smaller, the diffusion happens faster. So a good example is you can see that hydrogen ends up having the fastest diffusion. So the smallest possible option is the one that diffuses fastest through the material. You can even see it if you try to really compare apples to apples. So this is all the diffusion of different metals in silicon, and they're all even FCC metals. So you're not even putting in different types of atoms. And what you see is that as you go from copper to gold to silver to aluminum, your atoms are getting larger and your diffusivity is going down. And again, it's not going down slowly, it's jumping multiple orders of magnitude. And you can actually see this a different way. You can see it when you have a discontinuity in the diffusion rate, when you have a phase change in your material as temperature changes. So a good example is we said that iron can have different types of crystal structures. It can sometimes be face-centered cubic and sometimes body-centered cubic. An example here is that, so this is showing me as the temperature goes down or 1 over T goes up, the diffusivity goes down as we expect. Okay, this is an FCC iron. But then as we transform from FCC to BCC, the diffusivity flies up. Okay, and that just happens because we said face-centered cubic was a close packed structure. It had the most efficient atomic packing factor we could have, while BCC didn't. It had some empty space. Okay, so if you think about it, around this temperature, it'd be much faster to diffuse in BCC than in FCC. All right, The next thing we need to talk about is Fick's first law was talking about steady state diffusion. You can also have non-steady state diffusion, which means it changes not just as a function of position, but also with time. So in this case, we're going to have to describe our diffusion with a more complicated form, and we'll have to use a differential equation. So we're saying that the composition is a function of both the position and time. So we'll represent it as this differential equation on the right. So the derivative of composition with respect to time is going to be derivative with respect to position of our diffusion coefficient, and then also the derivative of composition with respect to position. If we assume that diffusivity doesn't change with location or local concentration, which is a reasonable assumption to make for solids, this becomes the form of Fick's second law that most people know. It says it has sort of a first a single derivative on the right and a second derivative, a single derivative on the left and a second order derivative on the right, right? Now, what this is describing is really something that we probably can sort of visualize anyways. So this is drawing that we have some infinite reservoir of material over here at this starting concentration. And we're looking at how this material moves into the system on the right, okay? And what we can imagine is as we go from T1, T2 to T3, so going longer and longer times, that species is going to diffuse further and further into the sample, okay? And we're just trying to describe the shape of that. This is putting a sort of atomic picture on it. So if you think about it, maybe you have something where you have your solid material, you have some gas species on the side with a given concentration, and you want to think about how fast those little atoms can diffuse into your solid lattice, okay? So we're not a differential equations class. I'm not going to force you to go and solve this. We're just going to use a simple solution. So this type of equation, this Fick's second law, can often be described with this solution shown here, which says that the composition at a given position x, so C sub x, minus the composition at 0. So what's the composition at sort of, C naught is infinite distance, so that's steady state. And then we'll, on the bottom, have the composition on the surface minus that steady state composition, okay? And that's going to be equal to 1 minus this error function, and then this term with the position divided by 2 square root of diffusivity in time, okay? You don't need to worry too much about this ugly thing. It actually is some gross equation. It's an integral with an exponential inside. We're not going to go and solve this. What we're going to do is basically just go and read what possible values are off of a table, okay? So if you go to table 5.1, it's on page 128 in the 10th edition of the book. You'll get a table which describes sort of how to read off values for this error function, okay? So it says that if the error function is equal to something, the value z is equal to something else. All right. So that type of equation can be used to describe many things. Physically, we could think about it as maybe we have some constant surface concentration of copper atoms here on the left. We're trying to diffuse it into some bar of material that we are trying to engineer with. We want to describe this change. One thing that's important to know is be able to describe what our boundary conditions are. So at time equals 0, the concentration in our sample here is going to be C naught for x from 0 to infinity. To the left of this, it's going to be that C surface, okay? And then, yeah, time is greater than 0. The concentration is going to be that CS at x equals 0. And then we know that C equals C naught at way out at infinity. But we want to describe all those other situations when x is neither 0 or infinity. So what we're really looking at is, this is generally what we want to solve for. So we want to solve for what's our composition at a given position or time, okay? And those positions and time are going to be in that error function equation. So let's look at a few examples. So I'm going to say we want to take an FCC iron carbon alloy with which initially has 0.2 weight percent carbon, and we want to do that surface treatment, that carburization, where we can try to change its surface properties. Okay, so what we're going to do is we're going to put it in an atmosphere that has a carbon concentration of 1%, 1 weight percent, and then we're going to wait for some given amount of time. Here I gave it to you as 49.5 hours. And at that time, we're going to take our sample out and we'll measure that the concentration is 0.35 weight percent at a position 4 millimeters below the surface. What I want to know is, what temperature did I carry that treatment out at, right? So I can go and use this equation to solve that. Now, if I look at this equation, I can think about what the problem gives me, okay? So my initial concentration, C naught, that's going to be 0.2 weight percent. C surface is the 1 weight percent. Time is giving to me, it's 49.5 hours. X is even given to me, 4 millimeters, okay? And then CXT is actually 0.35 weight percent. So that's what the concentration is at this given position of time. So it seems like I have everything there, right? Well, what's the problem asking? It's asking me the temperature. If I look, temperature is not directly in this. So what's the one thing I don't have? I'll give you a second to think. Yeah, the only thing I don't have in this is the diffusivity. So it turns out that I need to find that first, and then I can use that to figure out what my temperature is. So let's start plugging stuff in. So these are the things we talked about. We know what T position is. We know what C at a certain position is in time. We know what the surface concentration is. We know what the initial concentration is. We can plug that in and we can solve for the error function of Z. So I'm just going to leave, I'm going to call this Z for now, and we'll come back and solve for different things inside of it in a second. We'll end up finding that the error function of Z is equal to 0.8125. I can go and use table 5.1. If I look at table 5.1, it only has discrete values. It doesn't have every possibility of every value in the world. And what I look at is I see that it only has error function. It doesn't have exactly that value, 0.8125. It has 0.7970 and 0.8209. Those are the closest I can get. Now I know my value is somewhere in here, so I can think about, okay, how would I figure out for this value of the error function, what's my value Z? And I'm just going to make an assumption, and I'm going to do a linear interpolation between these values, okay? So I'm going to say, I'm going to sort of draw a straight line between these two and these two and figure out what Z is, okay? Here is just sort of showing that. So I'm taking what's Z minus the low Z with the high minus the low Z that's available on the table. And then I plug in the values for the error function and all of those. I would solve that Z is going to be about 0.93. Okay. We have to remember that Z stands for something more complicated. It's the position divided by 2 times the square root of the diffusivity times time. I'm going to rearrange this to solve for the diffusivity. And then I can plug in all my things. The position, this 4 is just a constant. what's that Z value I found? What's my time? I had to have a conversion here so I can get the right units on it because I want it in meters squared per second. And I can find that the diffusivity is 2.6 times 10 to the minus 1 meters squared per second. I'm not done. I need to find out what temperature I'm dealing with. So to do that, I have to remember my Arrhenius style equation for diffusivities. I just solved for my diffusivity. I would need to know what D naught and Q are, but I really want to rearrange this equation to find T. Okay, so the first thing I would do is rearrange this to find T. And then I would need to figure out what my unknowns are, right? And if I know my material, I can go look up a reference for what those might be. So I'm talking about carbon diffusing in FCC iron. I could go look that up somewhere. I'm going to take it from table 5.2 in your book on page 131. So what you find is that your D naught for carbon in iron is 2.3 times 10 to the minus 5 meters squared per second. And your activation energy is 148,000 joules per mole. So I can plug that in. I can find that my temperature is 1300. If I pay careful attention to all my units in here, I will notice that that is Kelvin. And that tells me that this heat treatment happens at 1027 degrees Celsius. So I'm not sort of, I'm just methodically working my way through these equations that we've introduced. Let's do another example, same type of equation. So in this case, I'm talking about making a transistor. I want to diffuse phosphorus into silicon. And what I'm first doing is describing what the diffusivity is at a given temperature. If we are given the surface concentration as 10 to the 20 atoms per centimeters cubed and a 1 hour diffusion time, it is asking us to calculate the depth at which the concentration will be 10 to the 18 atoms per centimeters cubed. Okay, so this is saying what's that position X that something is happening, right? So the first thing to do, again, in the same way, is look at the problem and see what it gives me. So it gives me the diffusivity directly. It gives me the time, so that's 1 hour. It also gives me that surface concentration, right? That's that 10 to the 20. And it gives me what my initial concentration is. So that's C naught. That's going to be this 0 atoms per centimeter cubed. So I'm going to go and solve for the left side of this equation. In this example, they did something weird. It's usually 1 minus error function, and the Cx and the C naught are on the other side, but they just manipulated that 1 minus around. They just switched the side of the equation. Anyways, when I go and I plug this in for the left side, what I'm going to get is that Cs minus Cx divided by Cs minus C naught is going to be 0.99. I can set that equal to that error function x divided by those parameters that I have, right? And again, I have this term right here. What I want to do is I want to, again, find when that error function of z is equal to 0.99. I'll do it the same way I did in the last problem. So I'm just going to jump past that. So the z is going to be 1.82. And what we'll do is we'll set that equal to what's inside these parentheses right here, okay? And solve for x. We find that we are 1.76 times 10 to the minus 4 centimeters. That would be a reasonable answer. Alternatively, you could change your units. So maybe you notice that this is a really small number and say, well, I'm going to put it in a better choice of units. In this case, it's 1.76 microns. So the last thing I want to mention is that we saw how the size of that diffusing species can be pretty important, but it turns out that, and we also saw how the crystal structure. So for example, all things being equal, BCC diffusion will happen faster because there's more empty space. But it turns out that those other defects that we mentioned also can come into play and affect the diffusivity too. So this is showing some general orders of magnitude for the fact that if you have diffusion of some species upon the volume of your material, it's going to be many orders of magnitude faster along the grain boundary, and many orders of magnitude faster than that along the surface. Okay, so these are big changes, even though the materials are the same. A way you could see this is if you ran an experiment and you have some film of material, pure elemental A, but you know it has all of these crystal defects. And if you were to then put some fixed source of element B, maybe you deposit a film of element B on top, and then take the sample, heat it, and let it diffuse, what you would find is this interesting type of diffusion pattern. So the smallest diffusion length into the material is through the crystalline lattice. Next, you get a little bit more diffusion along the grain boundary, but you get the most diffusion at the edge of this piece where it's diffusing along the surface of the material. Okay, so just to summarize all the fun stuff we talked about today. So diffusion is going to be faster for open crystal structures, materials with weak or secondary bonding, smaller diffusing atoms, and lower density materials. Diffusion is going to be slower in contrast for closed pack structures, materials with strong bonds, and covalent bonding is a good example of that. If the diffusing species is large, that's going to lead to slower diffusion. Finally, high density materials also have slower diffusion. All right, that's it. I will see you in our Q&A section associated with this. Have a great day, and I'll talk to you soon.